That matches the 20 that I am supposed to have. So I don't need to do any more work. Now, just as a matter of practice, let's go ahead and assign formal charges and see where we are. So for the selenium, selenium has 6 valence electrons minus 4 dots minus 2 bonds for a total of 0 charge overall. The fluorine on the left, 7 valence electrons, 6 dots, 1 bond, so no formal charge there either. For the fluorine on the right, 7 valence electrons, 6 dots, 1 bond, 0 formal charge there as well. So none of these atoms are charged individually, and so the collective sum of all those formal charges is also 0, which means that what we're talking about here is we're talking about a molecule that's completely neutral. All of the atoms are neutral as well. All right, any questions about that one?
No.
All right, why don't you take a couple minutes and try to do the OCS. Just as a hint, point of order here, the carbon will be your center atom in this one. Go ahead, get out some paper, try to draw OCS, and see if you come up with the correct structure. And a couple minutes, we'll come back and look at how you did.
Could you also have the oxygen and carbon double bonded as well as the carbon and the sulfur?
So what I've drawn is the simple structure. Obviously, there's a mismatch between the number of electrons that I'm supposed to have and the number that are here. So what it comes down to is we know that we are 4 electrons over, which means that we need 2 extra bonds. That's one of the things we talked about yesterday. So the question is, where are those 2 extra bonds going to go? And how do we know which one actually is correct and which one's incorrect? So we're going to have to rethink our structure. It's just a matter of how do we rethink our structure. So the 3 possibilities, we could have a single bond to the oxygen and a triple bond to the sulfur. We could have the reverse of that, a triple bond to oxygen and a single bond to sulfur. Or we could evenly distribute those 2 extra bonds and make 2 double bonds. Now, which one makes the most sense to do? Which one should we do? All right, structure 1, structure 2, structure 3. Which one makes the most sense? Which one solves this problem? And in the best way?
Structure 1.
Okay. How do we decide between structures 1, 2, and 3? All right, Wyatt's got it. It's formal charge. Formal charge helps us to decide between these 3 structures as to which one is correct. So if we look at it from that standpoint, let's go formal charge on oxygen. 6 valence electrons minus 4 dots minus 2 bonds is a 0 charge. Formal charge on carbon, 4 valence electrons minus 0 dots minus 4 bonds, 0 formal charge. Formal charge on sulfur, 6 valence electrons minus 4 dots minus 2 bonds, 0 there as well. So all 3 of the atoms in this structure have a 0 formal charge. That's the way that we tell them apart, because that's not going to be the case for all of these. If I follow the same line of logic and reasoning on here, for oxygen, I would have had 6 minus 6 dots and 1 bond for a -1 charge. Carbon would have been okay. Still 4 bonds, no dots, no formal charge. For the sulfur, 6 dots or 6 valence electrons, 2 dots, 3 bonds, positive 1 charge there. And this would have been essentially the opposite with this set in number 3. So it's formal charge that drives the bus here. And the structure that minimizes formal charge as much as possible would be the one that is correct. So this is our correct structure. These, because of those extra formal charges, have some fundamental flaws to them, and are not usable for that reason. So that's what we have to think about. That's what we have to consider when we have these kinds of situations. Now, the good news for us is that there are some trends and some things that we can pick up on that will help us make these decisions a little bit more easily in the framework of formal charge. The first guideline that we can point to is that carbon likes 4 bonds. If carbon has 4 bonds, then it's generally okay. Our second guideline, the nitrogen group, tends to have 3 bonds and 1 lone pair. The third principle, the oxygen group, tends to have 2 bonds, 2 lone pairs. And finally, the halogens tend to have 1 bond, 3 lone pairs. And so what these are, this is basically your blueprint to how you get to a 0 formal charge. If that shows up, then that's what you'll end up seeing, is you'll end up seeing a 0 formal charge on those atoms, which is usually what you're striving for and what you want. And so we saw that. We see that in the selenium here. Selenium is in the oxygen group. The oxygen group tends to have 2 bonds and 2 lone pairs. Selenium meets both of those criteria. It has a 0 formal charge. The same thing with the sulfur, the same thing with the oxygen in this structure. Carbon usually doesn't have a choice in the matter. It's going to form 4 bonds. There are some rare occasions where it does not, but we kind of take each of those in turn. But if you're looking for kind of a quick way to evaluate formal charges on structures, that's the way to do it. Look at how many bonds does it have, how many lone pairs does it have, and if you follow along in those guidelines, that's where you're going to find success. That's where it's going to work out and make the most sense for us. All right, any questions?
No.
All right, then let's look at our next one. In our next one, we have I3 minus 1. So we have the triiodide ion, I3 with a -1 charge. From this standpoint, we've got 7 valence electrons times 3, and the charge, -1, gives us an additional extra 1 electron. So in total, we have 22 electrons in this structure. For triiodide, we are going to have iodine single bonded to iodine, and one more there. We're going to fill in our octets. So 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. If I add all of this up, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I get 20 electrons in this particular structure. Now I'm supposed to have 22. So right now my structure is deficient. If I have filled all the octets and I still have electrons to use, then I have to double check. I have to see where I can use those extra electrons. And the general rule of thumb is that the center atom is going to be the place that can accept those extra electrons. And so two-dimensional shape, not a whole lot of places to put them. I'm just going to kind of stash them here to the side. If I wanted to redraw this, I could. And that'll get more into what we talk about tomorrow. But I can kind of station these, you know, about 120 degrees apart on that center iodine. And now I've got 22 electrons instead of just the 20. Now, as Malaz and I were talking about in our start here today, what do you do when you have a charged structure, a charged particle? Well, there's two ways to approach it. You can either draw in the negative charge, and so the negative charge is going to be on this center atom. It's going to be a -1. I can just draw it in right there. And the way I know that, again, is using my guidelines. Halogens tend to have 1 bond and 3 lone pairs. Well, the bond and 3 lone pairs are both on the outside, so we know that these have no charge, no charge. The negative charge must be on the middle. We can calculate that. 7 valence minus 6 dots minus 2 bonds gives us that -1 charge. So we can show it this way, where we say, okay, here's the -1 charge on the middle, the 0 charges are on the sides. And if there's 0 charges, I don't actually have to show them. The other way to show it is by just bracketing. So if I draw the structure again, and put in my dots again, I can show charge over all by putting the whole structure in brackets and then writing the charge on the outside. Either of these forms is perfectly acceptable for an answer. Now, as I was saying, SmartWork specifically asks for this form. So if you try to find brackets in SmartWork, you're not going to. You're going to have to do it charge by charge. But if we're talking about a quiz or an exam, something where you're going to have to draw something on paper and then upload it for me, that doesn't matter as much to me. You can go either way. All right, any questions about triiodide ion? All right, that's sounding like no. So let's move on to ozone. And in ozone, I will warn you ahead here This is one that has a resonance structure, but go ahead and take, take 3 or 4 minutes and try to draw ozone yourself. With ozone, you've got 6 valence electrons times 3 oxygens, so 18 electrons in total. And as I mentioned before, there is a resonance here, so make sure that you show both forms of the resonance before you can consider it done. And when you finish, just either pop up and say that you're done, or just drop write done in the chat so that I know that we can move on.
Okay.
Done.
Okay. See 2 of you are done. Brett, Malaz, how are you doing?
I've attempted it.
I said I was done.
Okay, I'm sorry. Okay, then let's see how we did. Okay, so for ozone, you're going to have a single structure to start. And if we fill in everything on that single structure, what we end up with is 6, 8, 10, 12, 14, 16, 18, 20. So we end up with 20 electrons in the simple structure. So this is where we have to go back and say, okay, I need an extra bond. It's going to have to go somewhere. If it goes here on the left or here on the right, it really doesn't matter. It's arbitrary. That's the definition of resonance, is we have an arbitrary decision on where to put a multiple bond. So that structure is possible, as is the structure that I'm about to draw with a double bond going to the right.
Oh, yeah. That's how.
Okay. To show that they are resonance structures, I'm going to draw in a double arrow, put brackets around it, and that's all that there is to it. Now, if we were
I gave
going,
them triple.
I'm sorry?
I gave them triple bonds, and I couldn't figure out where to put the last two. I was short two.
Well, yeah, the reason you're short two is because you added one too many bonds.
Yeah.
Yeah. So, like I've been saying, the easiest way to go here, start with that single bonded structure, count up how many electrons are in it, and that's going to give you a pretty good indication about what you need to do next. If your single bonded structure has too many electrons in it, you got to start cashing in extra bonds. 2 electrons over means 1 new bond.
Okay.
And so if you had done that, you would have had 20. You would have realized I need just 1 extra bond. And that would have led you to, okay, does the double bond go here or does it go here? So from a formal charge standpoint, we weren't asked to do this, but we could. The oxygen that is double bonded falls in line with our 0 formal charge. So this one would be a 0. The oxygen in the middle has 3 bonds and 2 dots. So 6 minus 2 minus 3 would give it a positive 1. And the one that's single bonded, 6 minus 6 minus 1 would give it a negative 1 charge. And so if we were assigning formal charges, that's what we would end up doing. Doesn't ask us for it there, but if it did, that's how we would approach it. All right. Any other questions that we want to talk about with relation to Lewis structures and drawing these molecules? Okay, so what we're going to go to then is, now that we've seen a little bit about how to work with drawing these structures, now we're going to start to dig a little bit more into what the structures actually say and what the structures actually do. And so from that standpoint, we're going to look at the concept of polarity. Now, polarity, generally speaking, applies to bonds individually. And then what we'll get to eventually here is we'll get eventually to talking about molecular polarity, which is kind of a broader application of this bond polarity concept. So when it comes to polarity, we can talk about bonds in terms of their polarity. we have nonpolar bonds and we have polar bonds. Nonpolar bonds are when we have very even and equal sharing of electrons. So we have electrons that are being distributed very evenly, and each atom in the bond has a want for those electrons that is very, very even as well. Polar covalent bonds, on the other hand, is when we have uneven sharing of electrons. And this comes as a result of individual properties of the atoms in the bond, known as electronegativity. And so the more electronegative an element is, the more pull it's going to have on the electrons in that bond. And therefore, the more likely it is that the electrons are going to spend more time around that atom compared to other atoms in the bond. And so the concept here is electronegativity. Now, in terms of polarity, how's that look? Well, we can kind of think of polarity in bonds kind of the same way that we think of electrical charge in batteries. If you pick up a battery has a positive end and a negative end. And polar bonds are similar in that kind of way. They have a positive end and a negative end. And we can depict the positive and negative ends in two ways. We can show it through arrows. Arrows like this point to the more negative side, and we get that little cross up here to show that this is the positive side of the bond. And so what we see in these, more electron density on the negative side, less electron density on the positive side. Now, the other way that we can depict this is with these funny looking letter D's. These are the lowercase Greek letter delta. And instead of showing arrows to indicate positivity or negativity in a bond, we can use these lowercase deltas, delta positive, to indicate the area of less electron density, delta negative to indicate the area of greater electron density. Now, how does that actually show up? What does that look like? Well, we have three examples here. These are called color density maps, electron density maps, where we use color to indicate the attraction of electrons. And so we can see in chlorine, where chlorine is sharing with another chlorine atom, the results here are pretty uniform. We can see that for the most part, the electrons are being shared pretty evenly between these two chlorine atoms. The range of colors is pretty much from, very, very pale green to very, very, yellow green. Not a whole lot of variance or change there. As is the case with hydrogen chloride, we see polar covalence there, and we can see that our bars have increased a little bit. I see a greener area here around the hydrogen, an orangish area here around the chlorine. And so what we're getting is a larger range of electron density and unevenness of sharing. And then when it comes to looking at the the ionic bond, like in sodium chloride, we can see that the chloride has completely separated itself from the sodium. The sodium practically has no attachment to that electron whatsoever because it's given it away. The chloride has all of the attachment to that electron because it has taken it. And so we can see that these three tiers, kind of nonpolar, polar, and ionic, have different kinds of impacts on how well or evenly or unevenly those electrons are shared. Now, as I mentioned before, the concept here deals with something called electronegativity. And in particular, when we look at bonding and the polarity or non-polarity of a chemical bond, what we start to look at is the difference in electronegativity between the two elements in the structure. As we saw in the previous slide, ionic compounds are featured with a total separation of charge. The electron completely leaves one of the atoms and goes to the other. Whereas in the polar covalent, we had a partial separation of charge. The electron was more likely to be around the chlorine than it was around the hydrogen. But there was still quite a bit of affinity for the hydrogen by those electrons. They were not completely dissociated from them. They were not completely taken away from them. And so the electronegativity scale, which helps us to kind of figure this out, was developed by a man by the name of Linus Pauling. And Linus Pauling came up with a way of determining the relative ability of an element to attract electrons to itself when it was in a bond. Now, these numbers here, these are what we call electronegativity differences. And the difference in electronegativity tends to fall into one of these three categories. If the electronegativity difference is less than or equal to 0.4, we generally can consider that bond to be nonpolar and covalent. Good examples of this are things like, obviously, any homonuclear bond where we have the same atom bonding to another atom of its kind, oxygen to oxygen, chlorine to chlorine, bromine to bromine. Those are going to be nonpolar covalent because the electronegativity differences there are zero. But what we'll also see is that this applies also to things that have very, very close electronegativities, things like carbon and hydrogen. Carbon and hydrogen electronegativity differences actually are right around that 0.4 value. But the bonds themselves, even though, are pretty much considered nonpolar. And the molecules that they form pretty much are nonpolar as well. This is the basis for most of what we know as organic chemistry. Carbon and hydrogen bonds together to make a whole big series of molecules. When our electronegativity difference is in that 0.4 to 2.0 range, that is when we consider things to be polar covalent, where we have uneven sharing of electrons, but we still do have sharing of electrons. And then last but not least, if our value is greater than 2.0, we generally consider this to be ionic. Now, a couple of important notes here. First of all, the distinctions between these three are nuanced. We're giving you general cut lines here as a way to try to help you to frame what it is. But if you come up with something that's 2.1 as opposed to 2.0, the difference there is not so pronounced that you immediately go, oh my goodness, that's ionic. We see there's a lot of variability. There's the lines here are fuzzy, they're blurred, they're not distinct and discrete. So we use them as a general rule of thumb, but they're not going to be super discrete. We're not going to be able to make massive generalizations based off of them. So this is the Pauling electronegativity scale. And you'll notice that pretty much every element is included in that electronegativity scale, other than obviously none of the noble gases are there, because none of the noble gases are reactive enough to form covalent compounds, or any compounds for that matter. So their electronegativities are unimportant to us. And we also can see that we're not including in here any of the rare earth metals. We're not going to include any of the post-actinides. So all those radioactive all those radioactive elements that we see that line up this last row of the periodic table after lawrencium, none of those are going to be figured in here. What we can see is that non-metals tend to be more electronegative than metals are, and that makes sense. After all, non-metals tend to want more electrons because they are closer to filling their octets than the metals are. Metals have a lack of want for electrons because, well, they're pretty close to noble gas configurations if they lose electrons rather than gain electrons. And so we see a general scale kind of going in that way. But obviously, fluorine and oxygen are the most electronegative elements that we have. And so, generally speaking, if we see one of these two elements in a molecule, we know that that's the way that the electrons are going to start pointing themselves. And so that's just something to keep in mind as we start to evaluate polarity, both in the molecular and in the bond kind of sense. All right, so before we get to bond length and strength and energy, let's go ahead and take a break. And we'll come back in about 10 minutes. Let's come back at let's come back around 10:05. And we'll finish up with bond energy and bond strength, which will take us through to the end of chapter 4, as we talk about how we can use bond strength to evaluate the energetics of a chemical reaction. And if we have any time left over at the end, we'll start to look a little bit into molecular shapes and structures. But 10:05, let's come back. With bond order, we're talking about how many bonds are there. So is it a single bond, a double bond, a triple bond? And obviously, the more bonds we have, the more electrons that they're sharing, the greater the attraction will be between the two atoms, and the more they're going to be pushed together. So both of those factors come into play here when we talk about the ideas of bond length and bond order. Bond energy is also tied to both of these. In bond energy, we're talking about how much energy does it take to break that bond and separate those two atoms from each other. And there are a lot of factors that go into that as well. But the ones that we can look at the most commonly are the bond length and the bond order. Bond length and bond order tend to have a relationship with bond energy. Bond energies will increase as bond order increases, and again, that makes sense. The more attracted these two atoms are to each other, the more electrons they share, the harder it's going to be to pull them apart. Likewise, if the atoms are close to each other, if they have a short bond, it will also be difficult to break them apart because the closer they are to each other, the more attracted to each other they are. That goes back to our discussion of Coulomb's law from yesterday. And so we can add one little thing to this. And it's that bond energy is going to increase as my bond length decreases. Again, that's an important statement to make because it speaks to the general idea of what we see in our relationships here. Bond order, bond length, bond strength, they're all related to each other in some kind of way. And so we see that this is a table of values for a bunch of different bonds. And we can see the impact of bond order. So if I go from a carbon-carbon single bond to a double bond to a triple bond, notice that my length is going in a downward direction. And notice that my energy is increasing with the bond order. So the bigger the bond is, the more my bond energy is going up. Now, what we can also see is the effect of the size. We know from our periodic trends that nitrogen is a smaller atom than carbon is. And so since it's a smaller atom here, we're going to see that it has a smaller bond length. And usually that means that it's going to end up having a smaller or a larger bond energy. But there are some other dynamics that go into this as well. Again, the thing with general trends is they are general, they are not specific. So sometimes there are other factors that have to go into play here. But what we can see is that as we go from carbon to nitrogen to oxygen to fluorine, our bond length decreases, decreases, decreases. And with the exception of this little spot right here, we see increase in energy, increase in energy. And this is the case all the way around. My bond length goes down, my bond energy goes up. My bond length goes down, my bond energy goes up. And like I said, there are some places in here that there are little exceptions, but that is the general kind of trend that we notice. Now, how do we use this information? What kinds of information do we pull out of this? Well, one of the things that we can do is we can use this information to figure out what the actual energy, the enthalpy of our reaction. So how much heat is transferred in our chemical reaction. We can actually estimate this using bond energies. And the way that we can do that is if we evaluate all of the bonds that are there in our reactants, and we compare that to all the bonds that are there in our product, we can compare the two against each other, and through that comparison say, okay, the bonds in the products have more energy. That energy had to come from somewhere. It must have come from the outside. So the overall energy is positive, which is an endothermic reaction. Or conversely, we can say, hey, the products have less energy than the reactants did. And so they must have released that energy as the reaction proceeded. That's an exothermic process. So what we really get into here is through the bond energies, we can estimate delta H. And the conventions that we've talked about as far as our sign are concerned apply here as well. Breaking bonds requires an input of energy. Input of energy is a positive energy. Breaking or forming bonds is going to release energy. The release of energy comes off as a negative energy. And so when our total reaction has a negative energy, that means that energy has been released from the reaction. We call that an exothermic reaction. When energy has to be brought in to allow the reaction to occur, energy input is positive. That's an endothermic reaction. And so we can calculate this using this equation. And the equation here is that delta H, the enthalpy of reaction, is equal to the sum of all of the bonds that are broken in the reactants and subtract from that all of the bonds that are formed in the products. So what does this have to do with Lewis structures and molecule drawing? Well, in order to know what kinds of bonds are being broken and what kinds of bonds are being formed, we have to know what the molecular structure looks like. And so if we have a reaction like this, we can use it to figure out our bond enthalpy, or excuse me, we can use our table and our structures here to figure out the actual enthalpy of the reaction. So what I like to do in problems like this is I kind of start drawing lines. So here are my reactants. So these would be the bonds broken. And over here are my products. These are the bonds that form. And so I can start doing an accounting of what's there. I have one nitrogen to nitrogen triple bond. And I have 3 hydrogen to hydrogen single bonds. On the product side, I'm making 2 ammonias. Each ammonia has 1, 2, 3 nitrogen to hydrogen single bonds. So on this side, I have 6 nitrogen to hydrogen single bonds. And so to address this, I'm going to go back to that slide that had, and I'm going to look up the values that I need. So the nitrogen to nitrogen triple bond, that was 945 kilojoules. Per mole. And I have 1 mole of nitrogen. Hydrogen to hydrogen single bond, 436 kilojoules. 436 kilojoules per mole. And I have 3 moles of that because I have 3 of those types of bonds. And then finally, nitrogen to hydrogen single bond, 391 kilojoules per mole times 6 moles. So go back now to where I was, start adding together these values. On the reactant side, 945 plus 436 times 3 gives me a grand total of 2,253 kilojoules for the bonds that were broken. On the product side, 391 times 6 gives me 2,346 kilojoules. So delta H for the reaction is going to be 2253 minus 2346, which would be a negative 93 kilojoules. And again, the sig figs for that one, since we are subtracting, the ones place is what is maintained because the ones place is the last digit in each of those values. So we round to the ones place, which gives us our negative 93. All right. Any questions about this example? All right, let's take a look at another one then. In this one, I've got formaldehyde, CH2O, reacting with oxygen to make water and carbon dioxide. Now, before we get into anything else, we got to make sure that this thing's balanced. Got 1 carbon, 2 hydrogens, 3 oxygens, so we're good. Okay, so what I want you to do, do an evaluation and split it up, figure out what bonds are here, what bonds are here, and what values you need to look up. And so let's take, I'll give you about 90 seconds to figure out what bonds we need to look up. And then for those of you that don't have the table handy, I'll go over to the table and let you look up the values that you need. So go ahead and take about 90 seconds, figure out what bonds are being broken, what bonds are being formed, and take it from there. All right. Everybody ready for me to move over? All right, if you're still working, go ahead and keep going. I'm going to start putting up processes and answers here on the screen so that as you start coming to answers, you have an idea of whether you're in the right neighborhood or not. Okay, so there was a bit of a trick in this one. For whatever reason, the carbon to oxygen double bond in carbon dioxide is different in its energy compared to most other carbon to oxygen bonds. I personally am not sure of the reason, but I do know that that phenomenon exists, and that's why we have a different value, 799, for carbon dioxide compared to the rest of carbon oxygen, which is usually 743. So there is a little bit of a twist in there. There's a little bit of a trick that you have to be able to reconcile in order to get the right answer here. But if you do the calculations otherwise correctly, on the reactant side, you should get 2,067 kilojoules. And on the product side, you should get 2,524 kilojoules, which means that delta H of the reaction, which is the difference of those two, is going to be negative 457 kilojoules. And this does make sense. I mean, compared to the last reaction that we had, combustion reactions are more exothermic. Combustion reactions are generally quite exothermic because we're talking about something catching on fire. And so when formaldehyde catches on fire and produces these products, This is the result, and we get a good bit of heat. And actually, for a combustion reaction, this is relatively low. We usually see significantly higher than this because there's a lot more carbon and hydrogen to burn. Any questions about this example? All right, so this is the end of chapter 4 for us. And so again, chapter 4 really focused on very, very hard on the drawing of molecules, the setting up of bonding structures, and that kind of thing. That's the primary focus. And so as you're working on the homework assignments, which the homework assignments due Thursday night, the quiz for chapter 4 is due Friday night. These are the things that you're going to want to pay attention to and take care of. Overall, if you can get the idea of molecule drawing down, and you can do it relatively quickly and accurately, what this really sets up, chapters 4, 5, and 6 have a lot to say about each other, and that's why we've blocked them together as a unit in this grouping. Chapters 4, 5, and 6, those cover molecules, molecular structures, shapes, bonding, and then what we'll start getting into in chapter 5 is the idea of molecular polarity, which we'll use to determine what causes molecules to stick together when we have a whole bunch of them in a substance, and that's what chapter 6 is all about. So we're kind of at the beginning stages of a larger discussion that's going to take us through more or less what we would consider midterms here for the course. So that's going to pretty much take us through the end of the week and spill over a little bit into Monday, but not too much. So with that in mind, I've got a few minutes. What I'd like to do is let's start looking at chapter 5 just a little bit. We're going to just kind of dip our toes in the water here. And like I said, for tomorrow, if you can get your hands on some balloons, and I'm talking about just your generic party balloon that you get a big pack of at a dollar store or at a someplace like that. That'll do a lot to help with the visualization and manipulation of these molecular shapes that we're going to be discussing. So with regard to chapter 5, it's usually customary for us to start to look at chapter 4. And so let's take a moment. I'll give you a couple minutes. Let's draw the Lewis structure for nitrogen dioxide. So go ahead and draw that out. And when you're finished, just give me a verbal "I'm done" or write it in the chat so that I know that we can move on.
I'm done.
Done.
I'm done.
All right, let's see how we did. So we're dealing with nitrogen and oxygen. And so what we would end up working with is a kind of an odd structure. Oops, went crazy. So 2, 4, 6, 8, 10, 12, 14, 16, and just that one single dot for 17 there. And so this is a rare case where not every atom fills its octet in the structure. And the reason why this one doesn't is, well, it can't. It's got an odd number of electrons, and if I have an odd number of electrons, that is always going to mean that somebody's going to be left deficient. Now, which one gets left deficient? Well, that goes to the one that's the least electronegative, and the least electronegative here would be the nitrogen as compared to the oxygen. So there is a resonance structure here. That double bond can be on the other oxygen just as likely as it is on the first oxygen. But the nitrogen is going to stay in that state. And so from a formal charge standpoint, there is a positive charge on the nitrogen always. There is a negative charge on the oxygen that has the single bond. The double bonded oxygen is going to be 0, of course, because as we have established earlier today, oxygen wants 2 bonds and 2 sets of dots. So those are our structures. The question is, are these bonds polar? So if I look at the nitrogen to oxygen bond that I'm going to outline here in blue, is that a polar bond?
Yes.
Yes. You know, the way that we can tell is if we look at our Pauling electronegativities. The Pauling electronegativity says that oxygen is pretty electronegative. Nitrogen is electronegative also, but oxygen is more electronegative, and enough so that we can say that that's a polar bond. And if I went in the opposite direction and looked at this nitrogen to oxygen bond, I would come up with the same result, right?
Yes.
Nitrogen and oxygen form polar bonds. So that one we can answer definitively and affirmatively, yes. But these other 2 questions, well, we really don't know the answer to at this point. What angle are these oriented to one another? Well, if we look at the drawing, we'd say, well, they're set up in a straight line. They'd be 180 degrees apart.
Yeah.
Reality is, that's wrong. That's actually incorrect. And the reason why, can we determine if the molecule is polar? No, not at this point. So there are questions that we cannot answer yet. And the reason we can't answer them yet is because we aren't thinking about these molecules as they truly are. In a 2-dimensional drawing like this, it gives us the impression that molecules are flat, that they have no depth. And that's the problem. Molecules do have depth. They do have 3-dimensionality. And so while we can draw them in 2 dimensions this way and get an idea of how they're put together, a 2-dimensional representation doesn't really give us a full understanding of what the molecule actually looks like. and how it arranges itself in three-dimensional space. And so because of this, we need to start to advance our understanding. And that's where Vesper theory comes into play. Vesper theory, VSEPR, the valence shell electron pair repulsion theory. What the VSEPR, Vesper theory, says is that those molecules, those electrons in those molecules are going to repel each other. And in doing so, they are going to repel each other in such a way that they are going to push on each other to get as far apart from each other as possible. And so that's what we're talking about when we see this line here, minimizing mutual repulsion. We're going to get at those bonds as far apart from each other as possible in that three-dimensional space, so that they minimize their repulsion. They do not push against each other as much as they can. And this is the theory that ultimately helps us to predict the shapes of molecules, the shapes of ions, and from there we can get into, from their shapes, learning some more about their other properties as well. And so there's some key terminology that we need to make ourselves aware of before tomorrow. And that is, when it comes to molecular shape, when it comes to the shapes of these ions or these substances, there are two ways that we can describe the shape. The first way is something called electron pair geometry. Electron pair geometry basically takes all electrons, treats them as equal to each other, and talks about a general shape that they take on when they are arranged as far apart from each other as possible. So a good way to think about electron pair geometry is, this is a generic shape. We're going to start by talking about generic shapes. That is, if I have this many electron groups, this is the shape that they put themselves into to minimize their repulsion. Molecular shapes, on the other hand, are specific shapes. And what we mean by specific shapes is, we're talking, this is the actual way that the atoms arrange themselves. And so in a molecular shape, we ignore the non-bonding electrons in terms of their influence on the shape. And so in order to get to here, you have to know the electron pair geometry. This speaks to this. Electron pair geometry helps to dictate molecular shape. Now, once we know a molecular shape, we can also figure out its bond angle as well. And so bond angle is simply defined as the angle between the lines of the bonds around a center atom. So if I want to evaluate the bond angle in this shape, for example, I start at one atom, I go through the center atom, and I draw out to the other atom that I'm trying to measure. So bond angles always involve three atoms: an exterior atom going through the center atom to another exterior atom. And so if we got out our protractors from geometry class, we would measure that angle there. And in this case, that angle would be 109.5 degrees. In this representation of carbon dioxide, going from one outer atom through the center to the next outer atom, that would get me a bond angle of 180 degrees, something that's perfectly linear in shape. And so the last thing that we'll talk about today, to kind of set us up for our discussions tomorrow is the idea of steric number. Now, steric number just refers to the number of total electron groups on the center atom of our drawing. And it's the steric number that really dictates those electron pair geometries. So when we look at molecular shapes, when we look at bond angles, what we're really tending to look at is what's going on around that center atom. So the center atom becomes the most important part of our drawings in this case. And so if we come back to that drawing that we made for the nitrogen dioxide, where I had a nitrogen with a single bond and a double bond and a lone electron there in the middle. This would actually have a steric number of 3. Because even though it is double bonded in this direction and single bonded in this direction, for steric number, we actually don't care what the bond order is. What we care about is the number of atoms that are being bonded to by the center. And so I've got 1 electron group to this oxygen, 1 electron group to this oxygen, and 1 electron group for the part that contains that lone electron. And so when it comes to electrons, to non-bonding electrons, we consider them in pairs whenever we can. But if there is no pair to be had, a single electron that is unpaired also counts as a group. So this would be a steric number of 3, which would dictate an electron pair geometry. The geometry there is actually something called trigonal planar. And we'll talk more about that tomorrow. But you can calculate steric number for any of the molecules that you've drawn so far, whether it be today, yesterday, or in what's to come. All you need to do, count the number of atoms that the center atom is bonded to. So how many directions do those electrons go? How many atoms is it bonded to? And then if there are lone pairs on it, how many lone pairs are there? And each lone pair gets counted as its own contribution to the steric number. So if there are, take that triiodide that we looked at earlier today, where I had iodine bonded to 2 other iodines. If I'm looking at the steric number for this iodine in the middle, I can see that I have 2 other iodines that's attached to. And I also have 1, 2, 3 sets of lone pairs. So the steric number for this guy is 5. So this is going to take some getting used to. But the thing that I want you to think about as we go through this particular chapter, because we're going to talk about a lot of concepts in this chapter. But what I want you to know is that all of the concepts that we talk about in this chapter are all interwoven. They're all linked together. So what we talk about with steric number influences molecular geometry, influences electron pair groups, influences bond angles, influences hybridization, influences bonding structure. They're all interconnected. They're all interweaved together. And so from that standpoint, that's what you have to kind of keep in mind. Everything speaks to each other. If you treat it that way, it's going to be a lot easier to absorb the information. If you try to treat them as individual packets of information that you have to memorize separately, it's going to be a lot more difficult. It's going to seem like a much bigger set of concepts to swallow. So keep that in mind. They're all speaking the same language. They're all talking together. They're just using different ways and different lenses and different perspectives to discuss whatever it is that we're trying to discuss. So that's all for today. Any questions?